Thank you.
I stepped out.
Okay, folks, I'm going to go ahead and get us started. So I know that I've stated some of this before, but I'm going to constantly be referring back to bits and pieces throughout the term. When you started college chemistry 1, the first thing you did was learn everything you could about the atoms of the element. Then you moved on to combining those atoms of elements in a very specific ratio to develop compounds, and you learned a lot about the compounds. Then in chapter 7, 8, and 9, you focused on the reactions, and you started talking about chemical reactions. The first chapter dealt with balancing chemical equations, performing stoichiometric calculations with those chemical equations. The second chapter focused on being able to determine the state of matter associated with the reactants and the products in chemical reactions for precipitation reactions and acid-base neutralization reactions. And then you went on and you discussed redox reactions. And then the next chapter focused on thermodynamics and specifically focused on the enthalpy of a reaction. After that, we went back a little bit and we started talking about the states of matter in greater detail. And so the very last chapter that you discussed in College Chemistry 1 was gas laws. Then when you started College Chemistry 2, we focused on pure liquids in chapter 11. Chapter 12 was dealing with solids, which we skipped. And then chapter 13 dealt with solutions. Today, what we're going to do is we're going to finish up our discussion of solutions. And then we're going to go back to talking about chemical reactions. And when we start getting into the chemical reactions, which we will encounter at the end of today, we're going to start answering 3 key questions associated with chemical reactions. The first key question that we're going to answer is, how fast does a reaction occur? In studying that, we're going to talk about rates of reactions. The second question that we're going to answer is, to what extent does the reaction occur? In which case, we're going to talk about equilibrium. And the third question that we're going to answer is, does a reaction occur in the first place? In which case, we're going to talk about Gibbs free energy, and we're going to talk about redox reactions a little bit more. So that kind of outlines where we're going today, and then what we're starting today that we're going to continue with for the rest of the semester. So again, we're in chapter 13, which deals with solutions. And right now, what we're going to be doing is we're going to be using some of that information that we went over on Thursday, which was the concentration units, and we're going to be applying them to colligative properties. Now, with these colligative properties, you're going to have to answer some key questions. One question, the first question you need to ask yourself when you're dealing with colligative property is you need to ask yourself, is this a non-electrolyte or is this a strong electrolyte? Because we're going to treat those 2 categories differently. And then with the non-electrolytes, you're going to ask yourself, well, is this a volatile solute or a non-volatile solute? Because you're going to create the volatility differently. And so what we're going to do is we're going to start by discussing colligative properties of non-electrolytes. Then we're going to talk about colligative properties of strong electrolytes. So that is the plan for today. Now, since I am bringing up this concept of electrolytes, I got to go back to chapter 8 of College Chemistry 1 and bring up a couple of terms associated with an electrolyte. I want to remind you that an electrolyte is a substance that conducts electricity. The reason it can conduct electricity is because it contains free-floating ions. If you don't have free-floating ions, then it would not conduct electricity. Now, with respect to this concept of an electrolyte, we can divide things into 3 categories. The first is a strong electrolyte. A strong electrolyte is going to be a substance that dissociates entirely in solution to form ions, according to the definition in College Chemistry 1. Now, as far as the substances we discussed in College Chemistry 1 that fit this category, it means it's either going to be a soluble ionic compound or it is going to be a strong acid. The second category of electrolyte is that of a weak electrolyte. A weak electrolyte only partially dissociates in water to form ions. And then that includes your weak acids and weak bases. And then finally, your non-electrolytes. And your non-electrolytes are going to be substances that do not dissociate to form ions in water. Now, we are going to broaden our definition slightly because instead of it just saying that completely dissociates in water, we're now just going to say it completely dissociates in solution to form ions. So we're going to broaden this definition so that the solvent system does not necessarily have to be that of water. Questions so far? So again, that's your very first question you have to ask yourself. Is it a strong electrolyte or a non-electrolyte? We're not going to worry about the weak electrolytes with respect to the colligative properties. So the first question, is it strong or is it a non-electrolyte? I'm going to first discuss the non-electrolytes, and then I'm going to come back to the strong electrolytes and help you with recalling a little bit about strong electrolytes. Now, this is about colligative properties, so I would be remiss if I didn't define a colligative property. A colligative property is going to be a property of the solution that depends upon the amount of solute particles dissolved in solution and not the identity of the solute. It depends upon the number of particles dissolved in solution and not the identity of the solute. I am emphasizing the word particles here. When a non-electrolyte is added to solution, it forms just one particle. So all non-electrolytes have just one particle. But when we get to the strong electrolytes again dissociate to form ions. Therefore, that means they're going to have more than one particle in solution. And so we're going to wind up treating them differently. Okay, so what are the colligative properties we're going to talk about? We're going to talk about 3 colligative properties. They are going to be vapor pressure, freezing point depression, and boiling point elevation. Now, with respect to the non-electrolytes, when you talk about vapor pressure, you're going to have a second question that must be answered. With respect to the non-electrolytes, there is going to be a second question that must be answered. And that question is whether the solute is a volatile solute or a non-volatile solute. Because again, we're going to treat them slightly differently. Now, with respect to the freezing point depression and boiling point elevation, it doesn't matter whether it's a volatile solute or a non-volatile solute. They're going to be treated the same. Okay. First of all, I want to remind you of what vapor pressure is, which you had on your first exam. Vapor pressure describes the pressure that the gas molecules apply above a liquid layer. So in this first example, we have a pure solvent. Only one type of molecule is showing. The solvent can gain enough energy in order to escape and form gas. It is this gas that is above the liquid layer that is applying the vapor pressure. Now, when you make a solution represented by the circles and the plus signs in the second example, what it does is it causes the vapor pressure to be lowered, meaning that there's going to be fewer solvent molecules that can escape into the gas phase. The reason that we see a lower vapor pressure is because of this idea that of entropy, this idea that nature tends to move towards mixing. And so it would rather stay in the solution phase where it is mixed than it would to be to go into vapor phase where it's not mixed. So again, one of the key things here is we are talking about the pressure applied by the gas above the liquid layer. And the second thing is that the vapor pressure of a solution will be lower than the vapor pressure of the solvent by itself. How do we go about calculating the vapor pressure of a solution? The vapor pressure of a solution is going to be equal to the mole fraction of the solvent times the pressure of the solvent. As a reminder, the chi of the solvent is equal to the moles of solvent divided by moles of solvent plus moles of solute. On Thursday, when I talked about mole fraction, the main mole fraction I focused on was the mole fraction of the solute. But again, you can do the mole fraction of the solvent. It is dependent upon what you need. And in this particular example, where we have a non-volatile, non-electrolyte, we need the mole fraction of the solvent. And so that is what we calculate, is the mole fraction of the solvent being in the numerator. Let's look at an example. Calculate the vapor pressure of a solution containing 38.3 grams of glycerin in 135 milliliters of water at 30 degrees Celsius. The vapor pressure of pure water at this temperature is 31.8 torr. Assume that glycerin is a non-volatile non-electrolyte and use the density of 1.00 gram per milliliter for the water. Okay. So if I'm wanting the pressure of the solution is going to equal the mole fraction of the solvent times the pressure of the solvent. I know to use this equation because I am dealing with a non-volatile non-electrolyte. Now, I'm not always going to tell you it's a non-volatile non-electrolyte, so how are you going to know it's a non-volatile non-electrolyte? Well, the easiest way is because there is only going to be one pressure in that problem. So you'll know it's a non-volatile non-electrolyte if there's only one pressure in that problem. Now, to be able to do this, I'm going to need the mole fraction of the solvent, which again is going to be equal to the moles of the solvent. Solvent divided by the moles of the solute plus the mole of the solvent. So I'm going to need to know the moles of the solute and solvent if I'm going to get the mole fraction. So my first thing I'm going to do is I'm going to take that 38.3 grams of glycerin, and I'm going to convert that into moles of glycerin using the molar mass of glycerin. Which is 92 grams per mole. So 38.3 divided by 92 is 0.416 moles of glycerin. The next thing I need is the moles of the solvent, which is the moles of water. So I'm going to take that 135 milliliters of water, and I'm going to convert that into moles of water. First thing I'm going to need is the density of water in order to get that into grams of water, and then I can use the molar mass of water to convert that into moles of water. Which is 7.5 moles of water. Now that I have the moles of solute and the moles of solvent, I can get the mole fraction of my water. It's going to be equal to the moles of water, which is 7.5 moles, divided by the moles of solute plus the moles of solvent. Which I get 0.947. Now that I have the mole fraction, I can plug it into the equation and solve for the pressure of the solution. It's going to equal the mole fraction of 0.947 times the pressure of the solvent, which was 31.8 torr. And we get a value of 30.1 torr. Now, it's always good to See if your math makes sense. So how am I going to know if my math makes sense? Number one, on the previous slide, I said that the pressure of the solution is going to be less than the pressure of the solvent. Well, the pressure of our solvent was 31.8 torr. The pressure of our solution is 30.1 torr. So that checks. The second thing is looking at the moles of each of these two components. The water component was extremely high relative to the glycerin component. Therefore, when I got the mole fraction, the fact that it was 0.947, okay, that made sense. Finally, if that is close, since that is very close to 1, I would expect these two numbers to be very similar. If this had been far removed from 1, then I would have expected this number to be a lot smaller. But since they were it's close to 1, I would expect it to be very similar. Questions? Okay. Now, that was a non-volatile solute. Meaning, since given the word non-volatile, it means that none of the solute goes into gas phase. The next example, or the next piece of information, deals with a volatile solute. Volatile would mean that the solute goes into gas phase. So in this vapor pressure, in that gas above the liquid level, you're going to have two gases. You're going to have your solvent and you're going to have your solute. Therefore, this total vapor pressure above the liquid level is going to be equal to the pressure of your solvent plus the pressure of your solute that's in gas phase. Now, applying the previous equation for the pressure of the solvent in gas phase, that means it would be the mole fraction of the solvent times the pressure of the solvent. But again, we cannot just disregard the solute when we're dealing with a volatile solute. And so you have to add to that the mole fraction of the solute plus times the pressure of the solute. I will say these equations in this PowerPoint will be given to you on the test. Okay, so let's look at an example. A solution contains 50.0 grams of heptane and 50.0 grams of octane at 25 degrees Celsius. The vapor pressure of pure heptane and pure octane at 25 degrees Celsius are 45.8 torr and 10.9 torr, respectively. What is the total pressure above the solution? First of all, I know that the equation I'm going to use is going to be P solution is equal to the mole fraction of the solvent times the pressure of the solvent plus mole fraction of the solute times pressure of the solute. And the reason I know that I'm going to use that equation is because I have two pressures. So the question itself is guiding you to which equation you need to use. Now, as before, in order to do this, I got to get the mole fraction, which means I need the moles of everybody. So I'm going to take and I'm going to start with the 50 grams of heptane, 50.0 grams of heptane, which I'm just going to refer to as C7 at this point. I'm going to convert, well, I'll actually, here, I'll do it, the entire thing. I'm going to convert that grams into moles using the molar mass, which is 100 grams of C7H16 is equal to 1 mole of C7H16. Which is 0.5 moles of C7H16. I'm going to do the exact same thing for my octane. I'm going to convert the 50.0 grams of octane into moles of octane, with the fact that the molar mass of octane is 114 grams per 1 mole. Which is 0.439 moles of octane. Now I need the mole fraction of both of these. The mole fraction for C7H16 is going to equal the moles of C7H16, 0.500, divided by the moles of the solution, which is 0.500 plus 0.439. So it's 0.532. I'm also going to get the mole fraction of octane, which is going to be the moles of octane divided by the moles of solution, which is going to be 0.468. Now that I have the mole fraction of each component, I can use the equation and calculate the pressure of the solution. So my pressure of solution, again, is equal to the mole fraction of the heptane times its pressure plus the mole fraction of the octane times its pressure. So that's going to equal 0.532 times 45.8 torr plus 0.468 times 10.9 torr. And you get 29.5 torr. Now, as I said before, you should always see, does it make sense? In this particular case, the pressure of the solution should reside between that of the solute and that of the solvent. So when you're dealing with a volatile solute, the pressure should be between that of the solvent and that of the solute. So the fact that we got 29.5, that is good because that is between our two. Now, does it make sense from the standpoint of our two mole fractions? And the fact is these mole fractions are pretty close to half. So I would expect this number to be roughly between those two, almost halfway between those two. And it'll be a little on the higher side, but still it'd be closer to halfway between the two, and it is. So the numbers make sense. So again, first thing you need to figure out is, are you dealing with a non-electrolyte? The second thing you need to determine is whether the non-electrolyte is non-volatile or whether it is volatile. If it's non-volatile, you simply use the pressure of the solution is equal to the mole fraction of the solvent times the pressure of the solvent. If it is volatile, then you have to do the pressure of the solution is equal to the mole fraction of the solvent times the pressure of the solvent plus the mole fraction of the solute times the pressure of the solute. And the way you're going to know whether you're dealing with a volatile or a non-volatile is whether there's two pressures. Okay. So I said there were three colligative properties we're dealing with. The first is vapor pressure. The next is going to be boiling point and freezing point. To help visualize the expectation of how the formation of a solution impacts the freezing point of a solvent and the boiling point of the solvent, I've shown you the phase diagram. In the phase diagram, the inner lines represent the pure solvent. The outermost line represents the solution. Specifically, it represents how the introduction of a solute impacted the solvent. Because this is all about the solvent. How the introduction of a solute impacted the solvent. Now, what you'll notice is from the inner line, we move left. And if you'll recall, this is between the solid liquid layer, which is fine because we said it was freezing point depression. So we would expect it to go down. The other one, you will notice it increases. That is because we are dealing with boiling point elevation. Now, the difference between those lines is the change in temperature. So the difference between these two lines on the left would be the change in the freezing point. That is delta T subscript F. And the one on the right would be delta TB for boiling point. Now, the first thing I want to do, because you're going to see it multiple times today even, is delta. Delta means change in. And just like Q equals MCAT was the change in temperature, and it was T final minus T initial, this change, anytime you have delta, it means final minus initial. So if we're talking about the delta TF, we're talking about the final freezing point minus the initial freezing point. I mean, excuse me. It's it's the final minus initial. That just didn't come out right. But okay, so let's look at the equations to get you through this. To calculate the freezing point depression, it is going to be the molality times Kf, meaning we have to use yet another one of our concentration units. And to calculate the change in the boiling point, it's going to be the molality times Kb. Okay, molality we talked about, but what is Kf and Kb? Those are constants. Those are values you will be given in the problem, because I'm not expecting you to memorize Kfs and Kbs. Those are values that are directly dependent upon the identity of the solvent. In this table, this first piece is the Kf. And this other one is the Kb. Again, they are constants. You are not going to be asked to memorize these constants. You will be given the constants. These constants have the units of degrees Celsius per molal. Now, in order to perform calculations associated with these solvents, you also need to know the freezing point, the normal freezing point, and the normal boiling point. I will give you the normal freezing point and the normal boiling point for everything but water. And at this point, if you do not know, water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. You've got bigger problems. So, but for instance, benzene, I would give you benzene. I'm not expecting you to know benzenes, but I will expect you to know that of water. But anyhow, you will be given the Kf and the Kb. So let's look. trying to give an example of every type I can give. So, a glucose solution contains 74.22 grams of glucose in 455 grams of water. Determine the freezing point and boiling point of the solution. Okay, we're going to need 4 equations for this. The first equation we're going to need, let's talk freezing here, is we're going to need to know delta TF is equal to the molality times KF. But it doesn't ask for the change in freezing point. It asks for the freezing point. So the other thing you're going to have to know is the new freezing point is going to equal the normal freezing point minus delta TF. Now for boiling, you're going to need to know that delta TB is equal to molality times KB. But again, this doesn't ask for the change in boiling point. It asks for the boiling point. So the new boiling point is going to equal the normal boiling point plus delta TB. Why did I subtract delta TF and add delta TB? Because I remember freezing point, what? Depression, decrease. Boiling point, elevation, meaning increase. So you got to remember the words to help you with the equations. Now, to be able to do this, I'm going to need the molality, which is a 5th equation. Molality is equal to the mole solute divided by the kilograms of solvent. This is the only concentration unit where the denominator is about the solvent. So in order to get this, I'm going to have to convert 74.2 grams of glucose which I'm going to just write as GLU. And I'm going to use its molar mass, which is 180 grams, to convert that into moles. And that's 0.412 moles of glucose. Now I need the kilograms of solvent. I was told that we had 455 grams of solvent, which is water in this case. Convert that into kilograms of water with the fact that there's 1,000 grams in a kilogram. So we're talking 0.455 kilograms. Now I have the information to get the molality. That is going to be 0.412 grams of glucose. Moles of glucose divided by 0.455 kilograms. So it's 0.906 molal glucose. Now I have everything I need, along with using the table previously, to do the rest of this math. Delta TF is going to equal 0.906 molal times 1.86, and that's degrees Celsius per molal. Again, that came from the table on the previous page. So that's 1.69 degrees Celsius. My new freezing point is going to equal 0 degrees Celsius minus 1.69 degrees Celsius, or in other words, a negative 1.69 degrees Celsius. Delta TB is going to equal the molality, 0.906 molal, times the KB, which was 0.512 degrees Celsius per molal, which is 464 degrees Celsius. So our new boiling point is going to equal 100 degrees Celsius plus 0.464, or in other words, 100.5 essentially degrees Celsius. Questions? Again, the four equations at the top of this slide are the equations you use if you're talking about a non-electrolyte. Again, I will give you all the equations that, well, all the important equations will be given to you on your equation sheet on the exam. But you're going to have to know what to use when. You have to know enough about what's going on to know when to use what constant, when to use what calculation, and so on and so forth. So I would guess that the biggest question, I keep saying, you use those for non-electrolytes, use those for non-electrolytes. How do you know if it's a non-electrolyte? That's the hardest part to me. Well, the simplest way is to know who your strong electrolytes are. And since colligative properties are only going to be strong electrolytes or non-electrolytes, if it's not a strong electrolyte, it's a non-electrolyte. So let's talk strong electrolytes. Again, reminding you from College Chem 1, strong electrolyte dissociates entirely to form ions. The strong electrolytes you must know are your soluble ionic compounds and your strong acids. I'm going to make your life even easier, I think. You will be given your solubility rules. Folks, if you haven't guessed, I don't believe in just memorizing for the sake of memorizing. I believe in understanding what comes out of an equation. And that's more important to me, is if you understand when to use what and what it means. Those are the more important things than just memorizing equations. Because to be quite honest, you leave this class, I know from experience that unless you use it, you're going to lose it. But if you don't lose the concept, that's the battle. So yes, I don't believe in memorizing just for memorizing. Okay, so strong electrolytes again dissociate entirely to form ions. They'll be your soluble ionic compounds and your strong acids. I give you your solubility rules, but I will say I should back up just a little bit. I do make you memorize your strong acids because you're going to use them tons of times this semester. But there's only 6. I feel like that's much more doable. So the 6 you must know: HCl, HBr, HI, HNO3, HClO4, H2SO4. Those are your strong acids. Now, what do we mean when we say it's a strong electrolyte? For example, sodium chloride. Sodium chloride is an aqueous ionic compound, meaning it's soluble. Therefore, it dissociates to form sodium ion and chloride ion. Calcium nitrate, because of rule number 2 of the solubility rules, is a soluble ionic compound. Therefore, calcium nitrate dissociates to form calcium ion and 2 nitrate ions. Hydrochloric acid, which is a strong acid, dissociates entirely to form hydrogen ion and chloride ion. Meaning, there's none of this on the left in solution. What is in solution is what is on the right of these equations, and only on the right of these equations. Now, if we go back to the definition, was one of the first definitions I gave you today, colligative property. It's a property that depends on the amount of solute particles, but not type. Sodium chloride, because it is in solution, is sodium ion and chloride ion. It means that there's actually 2 particles in solution. Calcium nitrate, because it dissociates to form calcium ion and nitrate ion, means that there are 3 particles in solution, 1 calcium and 2 nitrate. Hydrochloric acid, because it dissociates entirely in solution, means that it has 1 hydrogen and 1 chloride, or 2 particles. Strong electrolytes, because of this statement, we have to treat them differently. We have to take into account that they actually form more than 1 particle. So how do we treat them differently? In their calculations, we add a Van Hoff factor. The calculations are almost identical, folks, to what we just were doing with non-electrolytes, except they include the Van Hoff factor. The Van Hoff factor is represented with an italicized lowercase I. And it literally is the moles of particles in solution divided by the moles of formula units. So let's take our calcium nitrate example on the previous slide. I said that calcium nitrate formed 3 particles for every 1 calcium nitrate. So 3 divided by 1 means that the Van Hoff factor would be 3. So what I was telling you when I said, oh, this sodium chloride forms 2 particles, that's its Van Hoff factor. Calcium nitrate forms 3 particles, that's its Van Hoff factor. Hydrochloric acid forms 2 particles, that's its Van Hoff factor. So we got to take this Van Hoff factor into account in our calculations. Now, I have to be, now this Van Hoff factor, what I'm describing to you is the expected Van Hoff factor. In reality, due to dynamic equilibrium, we don't quite reach full dissociation. Let's think about what's going on and why we would not reach full dissociation or full Van Hoff factor. Let's take sodium chloride. Okay, initially I have my solvent and I toss in sodium chloride. No problem. The sodium chloride is going to dissociate because there was nothing in that solvent to begin with. But as we increase those solute particles, increase, at some point, we're not going to get as much in as we're not going to get it all of our solute in, because we're going to establish a dynamic equilibrium where as fast as we're adding some, it's precipitating right back out. Meaning we hit the saturated level. So once you hit saturation, you have some going in and some coming that is precipitating right back out. And so the Van Hoff factor isn't quite there. Now, for our purposes, you don't have to memorize, you don't have to worry about those numbers unless it is on an active homework, in which case they will give you the number. But you're not going to have to worry about these numbers. Just focus on the expected. But do realize that we're not quite to the level of expected, simply because of dynamic equilibrium. Okay, before we get into the math, let me do the next slide, and then we're going to take a break and then come back. So again, we have to take that Van Hoff factor into account. The equations are essentially the same as for the non-electrolyte, but The Van Hoff factor specifically impacts the solute. So when we're talking about the vapor pressure of a solution and we're developing the mole fraction of our solvent, we have to take into account the Van Hoff factor when we're determining the moles of solute. Now, when we're dealing with the change in boiling point or the change in freezing point, we're simply going to multiply the equation by the Van Hoff factor. Okay, you need a break and my voice needs a break. So let's take a 10-minute, let's come back at 3:10. We should only be another 50 minutes max. Basically do some calculations and then get into the last two PowerPoints, which are much shorter. And so we'll come back at 3:10 and get started. That way, if you want to go get something from the vending machines, you have a little bit of time. Okay, and no, I don't want it. Okay, I managed to expand it. So, okay. So we were talking about colligative properties of strong electrolytes. Let's look at a couple of examples because I always like leaving you with an example so that if you get onto active homework or any other homework and you're working it, you have something to at least look back at and hopefully help. So calculate the freezing point and boiling point in a solution made with 10.5 grams of iron 3 chloride in 150 grams of water. Assume complete dissociation. Okay, so the first thing I realize is that when I'm talking iron 3 chloride, if I go to my solubility rules, the third rule in that says halides are soluble except lead 2 plus, silver plus, and mercury 2,2 plus. Since this is not an exception, it means it follows the rule, therefore it is soluble. So I'm going to take a moment and I am going to rewrite the equation, or I should say write the equation that is going on. That iron chloride is going to dissociate to form iron 3 ion and 3 chloride ions, meaning that we are dealing with 4 particles in solution. So that is going to be our expected Van Hoff factor. Now, the next thing I notice is I want freezing point and boiling point. So I'm going to have to use the equation delta TF is equal to the Van Hoff factor times KF times molality. And then I can use the new freezing point is equal to 0 because we are dealing with water minus the delta TF. For the boiling point, delta TB is equal to I times Kb times the molality. And then the new boiling point is going to equal 100 degrees Celsius plus delta TB. So before I can do this, I've already got my I value. I know what that is. I now need to know what the molality of this is. So 10.5 grams of FeCl3. We're going to convert into moles of FeCl3 by using the molar mass of FeCl3, which is 162.2 grams of FeCl3 is equal to 1 mole of FeCl3. So we're talking 0.0647 of FeCl3. The water, we would convert into kilograms of water because that's the molality is moles of solute over kilograms of solvent. We convert that into kilograms of solvent using the metric prefix conversions. And now we can calculate the molality. Molality is going to be equal to the moles of solute, 0.0647, divided by the kilograms of solvent, 0.150, which means it's 0.432 molal. Now that I have the I have the molality, and Kf and Kb are both constants. I can go in and do these calculations. So delta Tf is going to equal 4 times Kf, which is 1.86 degrees Celsius per molal, times the molality we determined was 0.432 molal. So delta Tf is 3.21 degrees Celsius. So our new freezing point is going to be 0 minus 3.21, or in other words, it's a negative 3.21 degrees Celsius. Ever wonder why they use salt on the roads during the ice? Because this just lowered where ice freezes from 0 degrees down to a negative 3.21 degrees. It takes longer before it reaches that temperature, and therefore it's less likely to freeze. Let's look at the next one. So, or the next piece, and that's delta TB is equal to 4 times 0.512, and that's degrees Celsius per molal, times 0.432 molal. So delta TB is 0.9 degrees Celsius. So our new boiling point is going to equal 100 plus 0.9, or in other words, 100.9 degrees Celsius. Questions? As you see, other than this first piece where I figured out the number of particles and including that in the equation. Everything else is exactly what we just learned. Look at this example. Calculate the vapor pressure at 25 degrees Celsius of an aqueous solution that is 5.50% sodium chloride by mass. Assume complete dissociation of the solute. Okay. First things first, I notice that I'm dealing with sodium chloride. Rule number 1 says that if it contains a group 1 metal, it is soluble. So that means sodium chloride is going to dissociate to form sodium ion and chloride ion, meaning we have 2 particles in solution. The next thing I notice is it wants the vapor pressure of a solution. So the vapor pressure of a solution is equal to the mole fraction of the solvent times the pressure of the solvent. Now, this is again where it changes is when we're dealing with the mole fraction of the solvent. The mole fraction of the solvent is going to be the moles of solvent divided by I times the moles of solute plus the moles of solvent. That is a multiplication. We have our I, but in order to do this, we need the moles of solvent and the moles of solute. Now, I do want to bring in, I liked this problem because it brought in something that we discussed on Thursday, which is the percent concentration. When I see 5.50%, one way to interpret this, and the most accurate way, is that it would be 5.50 grams of sodium chloride divided by 100 grams of solution. I won't, times 100. And if you'll notice, that 100 cancels out and you're left with 5.5. This method of viewing percentage is extremely useful in these types of problems. Because we can simply look at what's to the left of the equation. And what I see is I have 5.50 grams of sodium chloride. Which I can get rid of using the molar mass. I can convert that into moles of sodium chloride. And that is 0.0941 moles of sodium chloride. Now, the reason I wanted to bring this one back in is because I want to remind you that if you look at the mole fraction up there, it's the moles of solvent, not the moles of solution. In fact, you cannot get from grams of solution to moles of solution directly. You cannot get from grams of solution to moles of solution directly because a solution contains more than one substance. So you have to take that 100 gram, you have to take the fact that grams of solution is equal to the grams of solute plus the grams of solvent. So 100 is equal to 5.50 plus the grams of solvent, meaning that our grams of solvent is 94.5. Which we can then use to get our solvent. By using our molar mass to convert to moles. And you get 5.25 moles of water. Now that we have all this, we can get our mole fraction. The mole fraction of water is going to equal the moles of solvent, which is 5.25 divided by our I times the moles of solute, which is 0.0941, plus the moles of solvent. So our mole fraction is equal to 0.965. Now, if I hadn't had a mistake on this slide and I'd have given you the pressure, I would have then gone and plugged it into this equation where the 0.965 is multiplied by the pressure of the solvent in order to get the pressure of the solution. Questions? Okay. So I'm going to summarize real quick. I think I've got space on. Yeah, I did. You're going to ask yourself, non-electrolyte or strong electrolyte? If it's a non-electrolyte, you're then going to ask yourself, volatile or non-volatile solute? If it's volatile, then for the pressure, it's going to be P of the solution is equal to mole fraction of the solvent times the P of the solvent plus mole fraction of the solute times P of the solute. If it's non-volatile, then it's simply P of the solution is equal to P of the solvent, or, well, times the mole fraction. No matter which of these that you're dealing with, delta TB is equal to molality times Kb, and delta TF is equal to molality times Kf. I give you these equations on the test. Now, if it's a strong electrolyte, then P of the solution is still equal to the mole fraction of the solvent times P of the solvent. The difference is over here, when you're dealing with the mole fraction, it's going to be equal to the moles of solvent divided by I times the moles of solute plus moles of solvent. And I'm running out of space. Solvent. Now, over here, delta TB is equal to I times the molality times Kb, and delta TF is equal to I times the molality times Kf. I don't give you those equations. You got to know where to put I. Any questions? Okay. Now what we're going to do is we're going to move into rates of reaction. And tomorrow, what we're going to be doing tomorrow specifically is going to be related to what you will be doing in lab next Monday. I should say tomorrow, and I think Thursday, part of Thursday, is going to be related to what you're going to do in lab next Monday. So you'll already have all the information. So next Monday, I'm not going to talk. You're going to basically get to come in, get your dishes done, and get going. So, well, I shouldn't say that. I won't talk much. I will go over the waste and stuff like that, but I don't expect to go over a lot. Okay, rates of reaction and collision theory. So as I mentioned at the start of today, I am going to introduce collision theory briefly. We are going to take the big components of collision theory, though, and we're going to discuss them in more detail later on. So this is just a quick introduction to rates of reaction and collision theory. There are three things that impact collision theory, and the first is going to be concentration. Basically, basically what collision theory is it's, does a reaction occur? And the only way a reaction is going to occur is if reactant A and reactant B collide. If reactant A and reactant B don't collide, then you're not going to get a reaction. That's the entire premise. So on up here, on the left-hand side, you have only 4, say, of reactant A, and only 4 of reactant B. Sure, they're going to collide. But over here, you have 11 of A, if I counted correctly in my quick pass, and you have 11 of B. They're much more likely to collide over here because there's a higher concentration. So concentration impacts collision theory because the higher the concentration, the more likely the molecules are to collide. Now, that takes care of one piece of collision. But in order for a reaction to occur, they not only have to collide, but if I simply tap this wall, nothing's going to happen to it. Now, if I take a bulldozer to this wall, something's going to happen to it. Meaning I've got to encounter this reaction with more force. Well, in chemistry, force is a result of temperature. If I have a low temperature, these molecules, when they impact, they're not likely to do anything. They're likely to just stare at you. But if we have high energy, high temperature, then we're more likely to get a reaction. So if you increase the temperature, you increase the rate of the reaction. Because ultimately, we have to get over an energy of activation barrier. We got to get over a hump in order to make the reaction occur. We'll talk more about temperature impact towards the latter part of this chapter. The last thing that impacts collision theory is the orientation. In the top example, well, in both examples, I'm reacting carbon monoxide with an oxygen molecule. In the top example, when the carbon monoxide collides with the oxygen molecule, it does so where the oxygen of the carbon monoxide interacts with the oxygen of the oxygen molecule, which ultimately results in no reaction. In the second example, however, I've taken a carbon monoxide molecule and the carbon of the carbon monoxide molecule reacts with the oxygen. Since the carbon is reacting with the oxygen, it can cause the reaction to occur, and so we wind up forming carbon dioxide and a free oxygen atom. But if this molecule didn't, if these molecules did not collide with the correct orientation, we would not have gotten a reaction. So the orientation does matter. Now, we can't control molecules' orientation as far as the direction they're going to collide. That's an impossibility. But we can control the other two factors. So just as a summary, which is where collision theory is leading, or this particular set of slides is leading. If you increase the concentration, you're going to increase the reaction. The reason you're increasing the reaction is you're going to increase the number of collisions, and therefore you're going to increase the chance that they're going to collide with the correct orientation. We are going to be talking about concentration. We're going to start it today. We're going to work on it tomorrow and on Thursday, probably. Now, the other factor was increased temperature. If you increase the temperature, you're going to increase the reaction. Because if you increase the temperature, you're going to increase the number of collisions. But more importantly, you're going to increase the number of collisions with the correct orientation and the correct energy. Anytime we can increase the collisions with the correct orientation and the correct energy, we're more likely to cause a reaction to occur. Okay. So with respect to this concentration, we're going to look at it from three perspectives. The first perspective we're going to look at is from an instantaneous rate. What we mean by an instantaneous rate is the rate of reaction that occurs over a really short period of time. The second way that we're going to look at it is tomorrow we're going to talk about concentration using the method of initial rates. And the third way we're going to look at it is concentration versus time using integrated rate laws. Okay, so again, we're going to focus on concentration, and we're going to talk about instantaneous rates of reaction. The very first thing I need to do is explain what we mean by a rate of reaction. Folks, you may not call it a rate, but anytime you talk about the speed you're traveling in your vehicle, you are performing a rate calculation. If you talk about the speed at which you're losing or gaining weight, you talk about a rate calculation. Because what a rate is it's a measure, quantity, or frequency, where you obtain it by typically measuring one variable against another variable. When you talk about the speed you're traveling in your vehicle, the first measure is the change in distance. The second measure is the change in time. And that would be the rate. Now, as I mentioned previously, anytime we see change in, we represent change with a delta. And anytime I see delta, it means final minus initial. So in this particular case, we're looking at the final distance minus the initial distance divided by the final time minus the initial time. Now, if we're talking about rates of reaction and we're looking at concentration, then what we're talking about is a change in concentration versus a change in time. Now, in chemistry, and you need to know this if you don't already, because you're going to see it for the rest of the semester. If you see brackets, brackets mean concentration. That's how we indicate concentration, is using brackets. Now, with the rate of reaction, we also do have some sign notations. And really, these sign notations exist because a rate cannot be negative. Can you go a negative speed? No, you can only go positive speeds. Can concentration ever go negative? No, you can only get down to 0. The fact is, this negative, we use a negative for reactants because they are disappearing. It does not mean negative in the mathematical world. It means what's happening to them. They are disappearing. A positive in front of this equation means that it is products. Why? Because the products are forming. The other thing you need to know is a rate, an instantaneous rate is the speed at a specific time, a short period of time. And the rate at which the reactants disappear or the products form must be the same. You can't have them being the rate itself, this piece of information being different. So therefore, we do have to take our coefficients into account in the instantaneous rate. So let me illustrate, and then let me illustrate the math you can do with it. And then we will be done. Okay. So here I have the reaction of hydrogen peroxide with 3 iodide ions in an acidic medium to form the triiodide ion and water. Let's develop a rate of reaction expression for our reactants and our products. First of all, the rate equals. If you go back a couple of slides, one slide, I said it was the change in concentration over the change in time. So it's the change in peroxide concentration over the change in time. But because peroxide is a reactant, it is disappearing So we put a negative in front of it. That is equal to our our iodide ion. Again, it's a change in iodide concentration versus a change in time. But the iodide is a reactant, and so it is disappearing, and so we have a negative value. Now the fact is, this disappearance, the rate for this disappearance and the rate for this disappearance have to be identical. So we have to take into account that coefficient. And the way the coefficient is taken into account is by developing a fraction. That's going to be equal to our hydrogen ion concentration over a change in time. Again, it's going to be negative because it is disappearing. And we take into account that the coefficient by making a fraction. That is also equal to the product. So the triiodide ion over a change in time, but now it is positive because the products are forming. And finally, we can talk about our water concentration, change in water over a change in time. It's going to be positive because it's a product, therefore it is forming, but we have to make them all equivalent, and so we use a 1/2. This is the rate of reaction expression that takes into account the concentration of the reactants and the products. Now, folks, just because I've written out this huge equality, but I can take any two pieces of this equality and set them equal to each other. So my rate could be equal to -1/3 of the change in the iodide concentration over a change in time. Or I could say, okay, the rate is equal to a positive 1/2 the change in water concentration over a change in time. Or I could put any of the other two parts together. So I could say, okay, well, a -1/3 the change in iodide concentration over a change in time is equal to a negative, or let's say positive change in triiodide concentration over a change in time. In other words, that expression, once you've written that expression, you can take any two parts because it is simply an equality. What part do you take? Well, that depends upon what you need to solve for. So let's look at where you actually are solving for something using an expression. Consider 2-dinitrogen oxide goes to form 2 nitrogen gas plus oxygen gas. Express the rate of reaction in terms of the change in concentration of each reactant and product. So the rate is going to be equal to our change in dinitrogen monoxide concentration over a change in time. It's going to be negative because it is a reactant, and we do have to take into account the coefficient. So it's a -1/2 the change in dinitrogen monoxide over the change in time. That is equal to our nitrogen concentration, change in nitrogen concentration over a change in time. That is going to be positive because it's a product, but we again have to take into account the coefficient. And then finally, that is equal to the change in oxygen concentration over the change in time. Again, that's going to be positive because it is a product. The next thing says, in the first 15 seconds of the reaction, 0.015 moles of oxygen is produced in a vessel with a volume of 0.250 liter. What is the average rate of reaction during this time interval? The very first thing I want to make sure is, again, this means concentration, specifically molarity, and molarity is moles solute over liters of solution, just like you learned last semester. So what we're going to do is, since this is the oxygen, we're just going to take out just the oxygen portion. So rate is going to be equal to a positive of the delta of O2 over delta T. So my rate is equal to the concentration. So that's 0.015 moles divided by 0.250 liter divided by the change in time, which is 15 seconds. So the rate is 0.004. And that is going to have the unit of molar per second. All rates have the unit of molar per second. All rates have the unit of molar per second. Now, the last one asks you to predict the rate of change in the concentration of N2O. We know, yes, I know I'm about dead, rate equals a negative 1/2 the change in N2O concentration over the change in time. We just figured out the rate as 0.004 molar per second. So that's equal to a negative 1/2 times the delta of N2O over the change in time. So delta N2O over delta T is equal to a negative 0.004 molar per second. I meant 0.008 molar per second. Again, what this is telling us is that in 15 seconds, 0.008 molar of N2O is used up. Well, no, that's not in 15 seconds. 0.008 times 15. 0.12 molar. 0.12 molar of N2O is used up. Where that number came from is I plugged in that 15 seconds into the delta T, and I multiplied both sides through by it, and that's where the 0.12 came from. Questions?
And then go to the 0.008. You just do the inverse of -1/2, which is 2/1 to move it over.
I multiplied through by -2.
Are you supposed to active today or tomorrow?
Active gets posted tomorrow. It'll be posted between 9:15 and 11 o'clock tomorrow. With that, I am done for the day.